Hello everyone, welcome to today's knowledge webinar, Design for Additive Manufacturing with Spherene Metamaterial. And this webinar will explore how Spherene enables lightweight, surface-conformal, high-performance structures with efficient material use, isotropic behavior, and seamless integration into parametric workflows, all while significantly reducing design and engineering time. Today you'll be also discovering how Spherene's ADMS technology is revolutionizing additive manufacturing. And stick around to know more about this ADMS technology. Unlike traditional TPMS or latticing workflows that require complex formulas and unit cell calculation, Spherene's design tools are incredibly easy to use. You have to see this to believe it. So stick around. Today's presenter is Daniel Bachmann. He is the Chief Innovation Officer at Spherene, specializing in business innovation, user interface, and marketing. With a deep hands-on understanding of both digital and traditional manufacturing processes, he helps industries integrate Spherene to optimize lightweight structures, improve material efficiency, and enhance product performance. He is the person you need to talk to. And he's also a 3D certified instructor, so always a good thing. And now let me show you where you can find Spherene on our website. Just go to knowledge.com and search for Spherene. Knowledge is changing the way designers purchase 3D software, offering more choices, more freedom, best advice, and faster service. Everything easy and with no headaches. Check us out at knowledge.com. And now I'm going to share Daniel's screen so he can blow your mind with Spherene. We're just transitioning to Daniel's screen.
All right.
Here we go. We can see your screen, Daniel. Take it away.
Awesome. Welcome, everybody. And I'm really happy that you joined this webinar. I have to show some really cool stuff today, like world premiere stuff. I will show you Spherene version 2, the first time to the public. And later I will show you what we have cooking in the background. But first, let's introduce ourselves. I hope it works. These three guys here, we are Spherene. We are not really good with taking photographs, but we are good with taking matter as our business. So here you see our aluminium and eloxated aluminium and plastic part that is 3D printed. The three guys, to introduce them, this on the right is Christian. He's the founder, and he found Spherene on his kitchen table. I will show you pictures later. This is Ralph. Ralph is responsible for the coding of this crazy surface we are doing. And I'm Daniel, and I'm doing these things with you as of now. Now let me show you how it all started. One moment, I have to sync my screen. So we are a company founded in Zurich, Switzerland, 2018, and this is one of the paper models that Christian made. He made like hundreds, thousands of them, and it was found by accident while playing with these kind of paper parts. And at one moment, he found, okay, this is really stable, and we found that it is so stable and it doesn't also exist in the mathematical world of like TPMS and other minimal surface structures. So how to get this into a computer program and an algorithm with buttons, that was like a huge challenge, and I will show you today where we are at with Spherene version 2. But first, here is a representation. What is a minimal surface? So you have the sphere. You can see that it bows in these two directions, in the same direction. Then you got a sphere. If both directions, when you lay it flat and look from both sides, from one and the other side, you see it is a flat surface, it's a plane. And if the curves are curved in the opposite direction, then it's a minimal surface. There are a lot of minimal surface known as triply periodic minimal surface fitting in a unit cell, so to say, where you have a form that attaches most of the time inside of a cube to another cube and connects these surfaces together. But the difference starts after we discuss there is a minimal surface and we have two volumes. We do not work in a unit cell. Spherene is an adaptive density minimal surface. So it is an algorithm that automatically computes how a volume is filled. So let me just switch there. So nature, for example, fills volumes really lightweight with the minimum amount of material. 3D printing, additive manufacturing promises that you can have the same. So use production on site where you need the parts 3D printed with material that you maybe locally source and produce it only when needed. So that's something we are working on from the software side. Here you see the difference of a Spherene and a TPMS. Here, for example, we have a gyroid. So the gyroid is inside of the unit cell. So you can think of one cell here, and then you put a cube beside with the same cell, and you can fill beautifully a rectangle, a box shape. So it all fits inside here. The Spherene on the other side, on the left one, you see that we have all these, we call these volcanoes, looking out on the surface. Now let's go further and cut the form out, make it more spherical, and then you see gradually the gyroid gets even more difficult and complex and chaotic the more you change the shape. On the other hand, the Spherene fits any shape that is surface-conformal, and this amount of computation from a simple cube to a sphere or even more complex object takes the same amount of computation power. It's not more complicated to do so. You design the surface and Spherene just fits in. Here on the left side, we see the comparison of the gyroid and the Spherene when you cut it out of a more organic form. So the Spherene is mostly regular on the outside, like where the attachment points come on to the surface, as the gyroid is chaotic, as we have like this sinus cosine that will be cut away from the organic form. What that means for forces that you introduce or stresses, you have an even distribution inside of the structure, whereas of the gyroid, it is chaotic and you cannot really predict what happens. Then here we have some curves. I will not show you lots of curves today, but this one is a nice one, a comparison between a resin print with a Formlabs tough resin under compression. So we see the same amount of force, 41 kilonewton applied, and the displacement is significantly less with the Spherene. Now let's go further. It has two volumes, so you could fill it with air, with fluids. It has no pockets to catch resin or powders. It is very controlled, so you can control the wall thickness like an organic way. There is no cut. You can change the density also in an organic way and other parameters. So surface conformal means take any shape, press a button and get Spherene inside. Now, if you want to work with values that are in these complex structures as Spherene are, we made it as simple as possible to control how it behaves. So the first thing, we control the density with so-called D-stops. So if you know the aperture from photography, you know that you can change how much light you introduce through the lens. And when you change it from one stop to another stop, you will have the double or the half amount of light entering. That's the same concept, the same numbers you can use to ballpark the densities if you want to double it. And also the volume percentage, pore size, diameters roughly correspond to these values. So you have something to the hand to judge what is happening. So we have multiple fields that we can control. We can control the density fields that you see here. So we have a high density on this side and a low density on this one. The wall thickness goes from up to down. You can change the wall thickness as you want. And the surface bias means that you can almost get a stochastic lattice on the one hand, and on the other side, you can have really big holes with short so-called necks. And every value in between, so you can change and mix it however you like. Let's go through some curves. If you want, you can watch this video later and make screenshots and stop at these curves. I'm not explaining these. But I'm a visual guy. This stuff here is really interesting. So with tools like intact simulation for Grasshopper, you can have a simulation workflow inside of Rhino 3D and also inside of NTOP, where you can simulate what is happening inside the Spherene. Here we apply a diagonal force to this cylinder, and what we see is actually really the diagonal introduction, like it is a full material. What we also see is here on the outside that the stress accumulation is on the surface directly. It is not on the outside where we have these volcanoes. So if we would close this cylinder and make it a closed hull, we would have the whole stresses on the outside. But with Spherene, something completely different happens. So you can think your 3D printed material objects to have it open pore and profit also from this distribution of stresses along the surface. Now, what I will show you later in the demo is this, how simple it is. So you just have an envelope that can come from any CAD software. We will convert it into a mesh because our process is mesh-based, and the result is also a mesh. Then you set the requirements. So what kind of density, wall thickness, and surface bias you want to have. Surface bias means the ideal minimal surface is at a mathematical superposition where it absorbs most of the stresses that flow through it, and we can shift it to the left or right, like outside of this ideal position, and weaken it, and that is this surface bias factor. And then we click a button and out comes a Spherene. It's as simple as that, as you will see soon, and you can go really, really crazy, and it's for designers and engineers and tool builders. So this was a traditional CAD part that we Spherenified. So it comes from milling. As you see, you have the rectangle forms. We have made some kind of creative approach here to make it look more Spherene. But what we would do is we would think this part completely different and just think about where it is attached. But the form, how it is made, can look much more organic with Spherene. So this is just a part from CAD and spherenified, but usually you would think how to design for additive manufacturing, then you will design your parts differently. It comes out without supports. So on the inside of a Spherene, you do not need any supports. And on the outside, if you have some overhangs, you might need some, or in this case, we didn't do anything. This part came just out of the print bed like that, and we just shaked it off and cut it apart from the build plate. So now this is a metal part. What Spherene can deliver is printability in any material on any print method. So it can be FFF, it can be SLA, it can be SLS, it can be metal ceramics, whatever you throw at it. We didn't find anything that was impossible yet. We printed also titanium parts, super small bone implants, and recently a company from South Tyrol here in Europe printed. The company is Scavo 3D, by the way, check them out. They printed a concrete booth for their exhibition, and that is in architectural scale. So scale is also not a limit. So where can you load Spherene? So we have a plugin for Rhino 3D. We have a Grasshopper integration. We have an integration for Autodesk Fusion. And this summer, we will have an integration for NTOP. So you are able to make Spherene forms also in NTOP. That is quite cool. Now, if you purchase Spherene, you get an API key that works for Rhino and for Fusion. So no problem with that. You buy just one license and you get both. Now, let me switch the document. Let's see if that works. One moment, please. So I hope you see that one. So a couple of more slides, then I'm starting the live demo. So we are in the business of matter, and our matter we call a metamaterial, Spherene metamaterial. It is isotropic, as you have seen, so you can apply any force from any side and it will behave like a full material that is lighter. It conforms to any organic surface, so throw at it what you want and it will grow like that and organic, and it will always be the most stable surface that is possible. Also, if you think about crash tests, so you want to crash this thing and you crash just a part of the structure, we have so much redundancy inside that your part most surely will survive to drive home if it's a car bumper or anything like that needs to be really rigid. Here you see a picture of the change of density, how organic this works. So we do not have any cuts and we do not distort any unit cell and try just to make this spherical appearance wherever and however possible. Then we have some geometric modifiers where we can close up parts partially, fully, and we can add cavities, we call that are forcing the surface away, and we can open this cavity. So you see there's only one volume that is accessed. We can switch which volume we want to access. So then the last picture that I want to share with you is, if I can get it. It's that one. So we are not engineers, but if you just approach engineering with Spherene, just from ballparking it out in a just quite fast test, you get this. I will explain. If you are an engineer and know what to do, you can get really a lot out of it and exactly control what you want. So this output here is made inside of Rhino with Grasshopper on a cylinder where we apply force from the top. And we have here, as you see 11, you see a constant density on this cylinder. And you see when we press on it, we have a accumulation of stress on the bottom part. And then just very naively, we lessened the density on the top and made it more dense on the bottom. And what happened, you see that these stress lines go on the upside now, and we have lost some stress accumulation here. So we have only 70% of stress in this object with a mass that is 95% of the volume. So we saved material and have even less stress in a naive way without being engineers. So that's really cool to see. And the workflow I will show later with some screenshots how this looks inside of a Grasshopper. And now comes what you have been waiting for, or I hope so, you have been waiting for that. I will show you the first time to the public the new version, Spherene 2. And maybe you have installed it already, you see, and are familiar with this toolbar. And you might know the workflow, how it looks inside here. But how to install it? Let's go to the basics first. You open the package manager inside of Rhino, and then you search for Spherene Rhino and install it, restart Rhino, and you are in business. In the version that you are able to download right now, today, as of today, 9th of April 2025, you will have to download the toolbar yourself and install it. But Spherene 2 is coming out soon that will deliver a toolbar and a menu for Spherene automatically with the package. So let's switch right away to the new toolbar. We have new buttons, really beautiful design of Christian. What is also new, we have a menu here where you can, if you're a menu guy, you can check this out. You see the examples and the help file here, some utilities to administrate your account and so on. So what is new? We have this shiny button here, an inspector, and that makes the life really, really beautiful when working with Spherene. So if you have worked with it already, you will enjoy this one. I will do it now a demo. This is so fresh that I just today started working with it. So bear in mind if anything is not working, it's work in progress and coming soon. So let's start making a mesh sphere. That can be also any CAD model that you import. It can be a BREP. It will automatically be converted with our tool. So we have this sphere. Cool. Layer, default, no problem. Here we can start a new project by clicking on it. And now we can enter a name. By the way, you see I'm using the Mac OS X version. It works for Rhino 7, 8 on Windows and Mac. So you're covered there. So let's call this knowledge. Select this, we call it envelope. So you are guided with tooltips while you're working. So this generates a project. That's the layer with the project name. It contains a mesh, so-called envelope, and it contains a field, a density field. That is this number. This number means the volume of this object here will be 95% lighter or the result will have the volume of 95% of that volume. That means this number. So let's just, we created a sphere, we made a project, we press this button here, that is the compute button, and this starts the computation dialog. So here you can set what you want to see. What we have a so-called single surface that is just the minimal surface itself as a sheet. We have a solid surface that is a surface with a wall thickness. And if we do not specify a wall thickness here with a field, we have this density reference thickness. So now it will make a object with the volume 95% with a wall thickness of 0.4 millimeters. We are in Europe, we have millimeters. I have no clue how much that is in inches. Then we can colorize the single surface if we would like to, or we could colorize the solid surface, which I will do now. We can enter a part name if we would like. So start, for example, we can enter a note, and we have some 3D printing features I will cover later. Here you see your licensing stuff. Let's just compute. So here you see a output folder or layer called Spherenes. And while this is computing, you can just work on more, send more computations, and it will just accumulate here. Let's change to a better shading here. I will hide this envelope, and now this is the first result. So we see a single surface, so that's the sheet, the minimal surface itself, as I promised. Then we have the thickened surface with 0.4 millimeters wall thickness at a density 5.6. So the two colors show you the two volumes. So you can also think this being fluid or gas flow channels. Now, to change the density, you can just adjust this value in this point. To make a gradient, you can copy this point here, or you can create a new one with this add field point button, and then it will make a gradient. But now let's show the first new feature that is so cool that we have that. That's the inspector. That is our inspector. It has also the toolbar in it here, like doubled. If you just want to work with that, you can do. So you see here the active project. You can have multiple projects and you can switch between them. And here you have some views. So I can just say, okay, I just want to see no modifiers, no fields, and no spherenes. So now you see that we hit the layers of that. Now we want only see the output of this layer here. We got that, and we can show all density fields again. So this is a massive time saver. The other one is, if you click any Spherene object, you can click on it and you see stats. And it's a bunch of stats you can get out. So we can filter it. So what's the volume percentage? Boom, and you see the volume percentage. And you can add how many holes is it, so that the genus, for example, we have some values there. So clear the filter again, get the full view. If I want to change this value here, I just click on it. I can enter any value that I like, and it updates directly. So there is a little bug that I see. So it just duplicated the point, but let's not get stopped by that. So let's change this one to 5.6. Well, we delete these duplicates here. And so we have 2 points. What will happen? Let's make it a bit more extreme. And yes, delete that point. Let's make a gradient from 5.6 to 16. And I use these values from the d-stops, but I can also use any value in between. Let's compute that again. Density gradient. And we just use the solid surface only. And let's change the color scheme to something else. So computation starts again. And in the meantime, what would happen if we want to change the wall thickness from left to right? Okay, let's press this button and add a field point for the thickness, and add 1 point here, add another point here, and change this one to 2 millimeters. Delete the duplicate and compute. So you see now that we still wait for the result from before that just came in, and now we wait for the other result. So it's really, really fast workflow, but can get confusing if you have everything turned on. So we started with this guy here that is a constant density. Then we made the wall thickness change, and first we made the gradient for the density, as we see here. That's the name that we entered for the part. And we have this gradation of 5.6 to 16, as we see. And the next one is we added a wall thickness change from 0.4 to 2 millimeters. And actually, that must be the beta version that leaves me hanging. This should now, let's add a new point here. Thickness point, 2 millimeters. Edit here. I think this was just a viewport error before when I have the double points. But no problem, we just go ahead and compute it again. Let's delete that old result and wait for the new. So now let's change another field type. Let's add the surface bias so that we can compare what's happening. So, sorry, now we got the result back. So this one changes from 0.4 and obviously to 2 millimeters. Very cool. Now let's add this so-called surface bias. So another field point, surface bias, and make this 0.98. If you place only 1 point, you get a constant result. So what this will do now, it will change the appearance or the balance between the size of these holes, of these volcanoes, and the neck. So you can change the appearance of that. So let's make the opposite a negative value here and compute that again as a result. And wait for what's coming back. So now we have already 3 fields, 2 gradients to control that. And you see, maybe we spent like 5 minutes to build that and already have a crazy object that is impossible to model by hand or by usual just formulas or unit cells. And this holds up to the promise of our isotropy surface conformity. So what we see now on this side, we made the, the openings change compared to this one. So this has huge holes, huge volcanoes and small necks. And the other one has small holes and long necks. So you see that that gets also almost stochastic inside like a lattice. And you can drive that even further, but not too far. And this also weakens the structure, so you can make it more dynamic. So if you want to have it give a elastic property, this is the way, one way you can do so. So now let's delete that surface bias one or just delete the layer so that we have a more simple outcome. We leave the wall thickness in, I think, for the moment. So that covers the field points, density, thickness, and surface bias. Then we can also add field geometry. So let's go one further. So here you see the fields, density, thickness, just that you know what's happening. And I will close up these guys here. So that's the scene, how it's looking. Let's make a so-called cavity that will indent this object. Let's use another mesh sphere. And because it's fun, let's make two. And we have this. So I will jump over and use this geometry modifier, add cavity, and select one of these and select the other one. And what it did now, it added this cavities layer containing these two meshes here. And if I click on these two meshes in the inspector, we see front face, that is a flag. So let's activate it for one and have it deactivated for the other. So this activation, deactivation is choosing the volume that we will make a cavity into. You will see that visually right away when it's ready. By the way, here you see that it is computing the minimal surface first, the single surface. There's 6 steps, and then it will go through and thicken up the structure. And if you want to have fast density evaluations, so to get on the density you wish, you just can activate only the single surface and it will calculate much faster. And then when you're ready, you could switch to solid. So let's see that. So let's use this new thing here. So let's hide all the modifiers. That is so cool. And we see now that this cavity here has the bright gray volume, and the other one has the dark gray volume pushed away. So this is not the perfect minimal surface as the Spherene is in this context here, but it's still 3D printable without support. So you can make a cavity on the bottom here and it will self-support. So you can hollow out this sphere and have a very strong shell that you can print on a FDM printer, FFF printer, no problem. So really cool. So we have used the first modifier for using a geometry. Now let's go even further. Let's go crazy and use another modifier that we call boundary modifier. We use a text. That's the wrong. We write an S for Spherene. Place it somewhere and scale it up. That's nice. So what I want to do now is I want to have a surface where this covers like this S structure and closes it up on the Spherene surface. Let's make it a little bit bigger. So this is the envelope that we had before. So the object that we started with. And I will use the same envelope to make like surface changes. So I can use this add boundary for that, where I can thicken, close, or partially thicken objects on the outside. Let's do that. It automatically made a copy of the envelope, called it boundaries. So I will hide the envelope now. And I will use mesh split to cut this S out, delete whatever I do not need anymore, also delete the curve. Boom, so we are there. And this S here, if I click on it in the inspector, I see back face, front face, and some numbers. First, let's keep it simple. We want a hull thickness. We want to thicken this up. So that's this one, hull thickness. We thicken it up to 1.2 millimeters. Then the target thickness, that is when we have the Spherene structure. So you see, we changed the thickness using these two field points. But we can also say, please thicken up to this surface to a specific thickness. So now we want it to thicken up to 1.2 millimeters. And as we have 2 millimeters here, I will delete this point. So everything will have a constant thickness now. Let's go back. So we have a hull thickness that goes inside 1.2 millimeters. We thicken up the Spherene structure so that it is 1.2 over a distance of 1.2. And we have both of these flags on. Let's compute that. It's as simple as that. And let's do something more in the meantime while it's computing. Let's make an other boundary object. So I do the same, add boundary object, select this curve. And by the way, you can also enter the values directly here, but I will skip that. So now let's see, we have this boundary and still the S is another boundary that is overlapping. Let's make a curve and cut this object apart a bit. Something like that. And we make a copy of that. Put this here. And on the side, we make another curve. I'm going really fast here. Oops. Oh, that was too fast. So let's. Oh, I mean, perspective view. I don't want that. I want it to be in a side view. Sorry. So the curves to cut stuff apart. So on this side, we will cut that. And here we will do that. And we make a copy, cut the bottom part, mesh, split. Oops. We select this boundary object and cut it with these objects. This we don't need anymore, and the curves also not. All right, nice. Now, clicking on this, let's add the values for the hull thickness again. I just copy paste these values in for this real quick. So now these are all the same, our new parts. Now we will make some changes. So here we have these two flags, back and front face. So let's play with them first. On the top part, I will deactivate this. On the bottom part, I will deactivate the other one. And here for this part, I will set the hull thickness to 0. So it will be 0 walls, will not show up, but it will thicken up the Spherene to 1.2 millimeters. As images speak more than me, let's compare the first example, and we wait for the combined one. So here we made this hull happen, and it has a wall thickness or hull thickness of 1.2. And if we make a clipping plane, then hopefully we would see that it will thicken up to 1.2 millimeters over a distance of 1.2 millimeters. So this is the value of the target thickness and the target distance. We can also set the target thickness to be the same as the wall thickness, then it will be like perpendicular, and we can adjust an exponent. Let me just activate this object real quick. Oops. One moment. Here's my boundary. So with the distance and the target thickness and the exponent, you can control the shape of the attachment point, which is really cool. Now we got the next result back, where we have the combination, and I hope it worked out. It did. So let's just blend in the boundaries first. So what you see here, we have the boundary here with the front face deactivated. Let's inspect what happens. So wherever this geometry is touching the volcano inside, it will fill it up. But it can also leave out little holes. And on the opposite side, on the top, we made the opposite. We just left all the holes open, but we closed the in-between space wherever this boundary goes through. Pretty cool. Then on the side here, that's not so easy to see. Here we said, whenever you touch this surface here, don't close it up, but thicken it up, thicken the structure up. So that is what you see here. You see it like it makes this angled shape connecting. So we have a super complex object made in minutes. So that's a really, really cool thing. I'm super happy that everything works until now. Let's go even crazier. We have a new concept called detail geometry. Think of it as a Boolean modifier, so you can add or subtract a geometry. But you can also say, as we did with the boundaries, should the Spherene thicken up to that surface or not, or what should happen there? Let's go in a top view and make a quick pipe and make a hole through the structure. So something crazy. Pipe. Let's go. Make this big, make this small. Great. Don't need the curve anymore. Here we got the pipe. And what we have to do now, we place it somewhere. Oh, that is really crazy. I mean, Boolean this will be a crazy Boolean in any application. Also, what is new in Spherene 2, I hope this works now after I say that, we have a new meshing kernel that is really doing beautiful Booleans, and most 95, 98% of the outputs are watertight meshes. So that's really crazy that it works. So let's take this object here and make this a detail that is a heart-shaped icon here. And what this did, it made this detail object here. Let's delete the original one. So this is now a mesh. And let's extract the mesh part here. Delete that one. So details can only be, no, that is wrong. We need it closed. That is something else. So what I wanted to say is boundary objects can only be open meshes or open objects, while details can only be closed objects. So I almost did that error myself now. So this is a detail. And I click on it in the inspector, I can tell it, as with the boundary object, how to attach to that. So let's keep it at 2.4 here and make it a subtraction. And let's go ahead and compute that one. Let's name that detail. So this could be a cable channel that goes through an object, and you can, coming from CAD, you can design that whole structure and geometries that you want to use in CAD, import it into Rhino or in Fusion or later in NTOP, and just tell these objects what to do. So it's really easy to design with. So now, since it's hard to see, I will switch back and forth here. So we made this Boolean operation here, made a huge hole following this shape through that complicated Spherene object. I mean, how crazy is that? Model this in any other application with any other tool. I'm happy to see the results. Model something with Spherene, and I'm also happy to see what you do with that, because you can really do awesome things. So now this covers most of the tools. I want to show you some other things. So we have seen Spherene 2, the new geometry modifiers, the new inspector, new meshing engine. Let's do another trick, a last trick inside of Rhino. Let me just delete some of these things. No, not one last thing. I have more things to show. First, let's see what we have here. We're not finished with new things. We have a set thickness factor. So if you print in FFF, like on a Bambu Lab printer, for example, you come to the tops of the Spherene. Let's go here. At all the places here on the tops, you can adjust the scale in Z direction with this Z factor to make it a little bit thicker. And this gives you more layers to print on a Bambu Lab or any other FDM printer. So that's a new feature. Then we introduced mesh reduction. So you can have your mesh lighter. For example, if you have our high polygon mesh in final mode, final quality, a Formlab slicer or any other 3D slicer might be slow to slice. And if you reduce the polygon amount, you can use this one to make it much faster when it slices. Then we generate support points. So where you can print this sphere, it will add some support points. And I will show you later also a new announcement that nobody knows of. We open source a tool to do something. I will come later to that. Overhang correction, experimental. We are not magicians, but we are working on it. So here, what is cool? If you are in fluid dynamics, check this out. And now first, yeah, let's do that. Let's do first the labyrinth. If you're in fluid dynamics and want to do CFD simulation, you want to have two meshes of the two volumes where you can perform your simulation with. And we provide that mesh for you now. How cool is that? Let's wait for that to compute. And yeah, let's compute the other thing. I turn off the labyrinth and I just change this to RGB because this one can do some cool magic. So the result of the labyrinth is back. So we still have the solid surface as we know it, but now we also have one volume as an object, 3D object, and the other volume as a 3D object. So the space in between these two objects is this solid surface. And with the other ones, you can now perform fluid simulation that is with watertight meshes that we deliver now with the new engine. And it's beautiful that that works. So, other cool thing, this RGB mode here is looking crazy, but you can use it to composite if you are in computer graphics, or you can select this object and explode it. And this gives you access to the modules, how we build up this thing. So you have the outside rings, you have the two sides, and you can do whatever you like with that. We use it to, early I used it to paint supports on these things here for my Bambu Lab printer. Christian uses it for compositing and making things clear. Feel free to use that. So the colors that we have are not just a game. Now, Grasshopper, I'm not a Grasshopper guy. I will just show you that we have, hopefully, yeah, we have Grasshopper integration. So you have a bunch of nodes where you can assemble your Grasshopper script. Then what you also can do is you can drive all field points from simulation packages. So let's say you are a simulation engineer, you have ANSYS, you can export a CSV file and then drive the CSV data. You can drive the density, for example, or wall thickness. And even cooler is intact simulation for Grasshopper allows you to simulate a full body, generate a spherene and re-evaluate the spherene to make really fast in one window simulation approaches. And that concludes now the Rhino live demo part. And yes, I will switch to another slide because we are almost an hour in and I want to leave some time for the Q&A later. Let's go through that thing here. And I have to find the PDF. So we were here. Let's see. Okay, so this couple of slides show the simulation workflow, how you drive Spherene with simulation. You have input geometry with the intact simulation plugin. You can make the simulation with force applied and constraints and whatever. You drive the Spherene with it, and then you get the result of Spherene and simulate that again. So how does that work? Here we see a grab cat brake pedal. We press on this thing. Here is the input that is defined. So we have a material, an envelope, a restraint, the footrest, force, and the loads. And we simulate that. We get, after 30 seconds of the full body simulation, we get a first results that we can use to drive, sample some points, and then drive the density of the Spherene. So let's go there. We generate the Spherene. We see, oh, it might be cool, but here we have some issue. We need more density. So what do? Very easy to solve in Grasshopper. Just put in this curve modifier and drive the density at a specific point, adjust that. So we make the mapping, we remap the values so that we fill up this space that we had before. By the way, here you see the time, how much time this took. So we have 30 seconds, 1 minute for the first generation of Spherene, another minute for the second generation of Spherene. And now we added the boundaries. So that's just the geometry defining the outer shell with the wall thickness and attachment points. Took a little bit longer, but now it's a printable object. And let's take that one and simulate that one, that object with intact simulation. So what is cool with intact simulation is that it is voxel-based. It doesn't need a meshing and it's very fast and runs on your local machine. So this took 10 minutes because of the complexity and the cell size we needed. So what we see, we want to distribute the stresses a bit more. How to do that? Let's adjust the wall thickness with this remapping, recompute that one, and now we have distributed the stresses a little bit better, and we are there with the result. There are different approaches. You can make the solid body simulation, sample some points, then average the density fields, average the thickness, average all the simulation data that you get, and get an averaged result back that distributes the stresses. So this concludes that slide, and now I have the last announcement. Then we come to the Q&A. So before I told you that we have something new, let me see where that is. So we know and print difficult objects, and we are searching for solutions to do so. So here you see that tool or utility that I showed you before, where we can add support points, and we can also color areas where we know that are overhangs. Together with this information, with the painted vertex color and this point here, we can then, so these are the points only, we call them support points. We can then drive a 3MF export that will automatically now for Prusa slicer, Orca slicer, and Bamboo slicer paint the support areas where we can have supports generated only where supports are needed. And this saves a bunch of time, makes beautiful objects. It's not perfect, but it's really cool, and we are open sourcing it. Please feel free when we announce it to code and change stuff and make it better. It is not only for Spherene, so we developed this for Spherene, but you can imagine you have any Grasshopper object or CAD model you want to make a crazy support on it. You place some points, and together with the points and geometry, you select them, start a script, and you get the 3MF out to then generate supports. We are releasing the GitHub repository or announcing it, I think next week or in 2 weeks. We fix some small issues and make some nice README and make the code a bit verbose, and then it's free for everybody to work with it. That concludes now my demonstration about Spherene, and I'm happy to answer all your questions.
Thank you, Daniel, for this stunning presentation and for this breaking news about the open source, and also to showcase Spherene 2.0. Here, you've seen it here first at Novage. I just want to share my screen again with you to show you where you can find Spherene at Novage. Just go to novage.com. And don't forget, we also sell Rhino with or without Spherene. And yes, we're sticking around a few minutes if you have any questions. For once, I'm speechless, but we will hang out. And yeah, Daniel is, as you have seen, is the right person to ask. So he'll be a few minutes with us. And I want to remind everybody that Novage is changing the way designers purchase 3D software, offering more choices, more freedom, best advice, and faster service. So you can get your Spherene, your Rhino, and anything else you need for your 3D design. Daniel, I don't see any questions.
All right, all clear.
I think you covered a lot of things, and it was, as I said, the presentation was stunning, and the results of your design were really breathtaking. I want to invite everybody to share this webinar. It will be recorded and it will be posted on YouTube on our veg series. So just search for No Veg on YouTube. Thanks again for joining us today. Have a great rest of the day, everybody. Bye-bye. And thanks again, Daniel.
Bye. Thank you. Bye-bye.